Okay, so next we have Joseph Mohr, who will be talking about new galaxy cluster samples.
Okay, thanks a lot to the organizers for the invitation, the opportunity to speak. I'm talking more about how we produce the actual samples of clusters within the context of the new or relatively new large, deep, wide field surveys, optical surveys like DES and HSC. And the work that I'll describe is done largely by Dr. Matthias Klein and also two graduate students, Sebastian Grandis and Maria Paulus, and I'll try to always emphasize who's leading what. Also, Sebastian's played a major role in supporting this effort, these papers. So an overview, there are basically 4 parts of the talk. I'll probably just get to the first 3. Some preliminaries, then I'll talk about a new X-ray selected sample, RASS plus DES. I'll explain what that is in a minute. And I'll talk about the impact of DES on SPT cluster samples, and then end with some prospects for eROSITA cluster cosmology where we've done a forecast. The results that I'm presenting can be found in these 3 papers largely, and you can go there for more details. And yes, I've included a few slides on this eROSITA cluster cosmology forecast that if you're interested, even if I don't get to it, you can read it on the web page. Sorry, I'm thinking this is an auto. Okay, motivation. So we just saw that SC cluster surveys lead to very interesting cosmology constraints. That's also true for the X-ray. In fact, the X-ray cosmology constraints from clusters predate those from the SC. In addition to cosmology, if you produce these large samples, X-ray, SC selected, optically selected clusters, you can study the baryon content of clusters, you can study AGN feedback, which as we heard is important, has important implications for the cosmic shear experiment that's coming along. You can study the mass accretion history. I think that Professor Lin will tell us more about that in a talk up. So what's new here then is deep and wide optical survey data. I'm going to talk about the 5,000 square degree dark energy survey, but there's also the smaller area and deeper HSC and KIDS surveys available. The goal here is to understand how best to combine DES, but more broadly speaking, Euclid, LSST, HSC, with the SC and X-ray surveys that are coming to improve cluster selection. That'll be the focus of this talk, but also weak lensing mass calibration. Okay, so what about cluster selection? What does that mean? Well, the first step in finding clusters is the hardest part is to build an instrument that go out and measure the sky or map the sky at millimeter wavelengths. This is a millimeter map of the sky, or actually a simulation. You can see the large scale variations here are the primary C and B variations, temperature variations, and here, these small objects here are the galaxy clusters and groups. So to produce an SC cluster candidate list, one would simply do object finding on such a map. You'd have to do some fancy filtering. All of this has been, is well discussed in the literature, and there are techniques that are being improved to extract the clusters, or a list of clusters, their fluxes or signal to noise from these maps. In the X-ray, we have similar. This is doesn't look very impressive, but it's from the ROSAT All-Sky survey, the existing All-Sky X-ray survey. And here also you have different background noise characteristics, but you basically look for objects, measure their signal to noise of detection, measure their fluxes, and so on. And in the optical, here is a multiband image of a particular cluster at a redshift of 0.35. You find a whole bunch of galaxies in these clusters of similar color, the so-called red sequence galaxies. I'll say more about those in a moment. And you can use those to identify clusters and determine their redshifts. If you do SC and X-ray cluster finding, what I'll talk about most of the rest of the talk, you need the optical data to get the photoz's. And as I mentioned, you use the red sequence to do that. What is selection, then? How do you model selection or the mass selection? Because in the end, you want to basically use the distribution of clusters in redshift and observable, together with the halo mass function, which is cosmology dependent, to constrain cosmology. How do you model that mass selection? Well, that's easy to see here in this plot, which is the measured X-ray count rate versus a version of the virial mass, M500 critical, these are expectations for the eROSITA survey for different redshifts 0.1, 0.3, and 0.7. And so you can imagine if you come into a catalog created in the way that I just described, and you say, I'm interested in all objects above a particular count rate, you will basically make a cut in the observable. That cut in the observable, then, together with this distribution at this particular redshift, for example, maps into a mass completeness, which goes from 0 over here at very low masses up to 100% over here at higher masses. And the transition here depends on the distribution of scatter here, observed and intrinsic scatter, but is largely something approaching an error function, okay? So that's how we model mass completeness. What about contamination? So contamination it is a focus also of this talk, so I just want to say a few things. In SC samples, contamination, which means sources in the final cluster catalog that actually are not clusters, contamination comes only through noise fluctuations in the map. To reasonable approximation, the SC signature is lit up only in the clusters, in the cluster virial regions, and the rest of the universe is dark. That's not precisely correct, of course, but to reasonable approximation. Because this SC signal of a cluster is negative, it's very hard to mock up an SC-like, cluster-like signal without there actually being a galaxy cluster there. And so SPT cosmology samples, just from extraction from the millimeter wave map, start with something like 5% contamination. I mean, it depends on what signal to noise. This particular value comes from the SPT standard cosmology sample cut at 5 sigma. Optical confirmation of this sample that's then 5% contaminated then pushes the contamination to sub% levels. X-ray, the story is somewhat different. You get contamination not only through noise fluctuations in the map, but also through AGN. So the X-ray sky is largely filled with AGN. There are 10 AGN for every cluster, roughly speaking. And so it's important to be able to separate the AGN from the clusters. If you have good angular resolution in your X-ray images, then you can simply look for point sources. Those are the AGN. Extended sources, those are the clusters. When you do that, studies by Viklinen and others have shown that you can produce an X-ray selected candidate list that's about 10% contaminated, and then, so a little worse than SC, but not much. And then when you do optical confirmation on that particular sample, where optical confirmation means look for an optical counterpart behind every one of these X-ray cluster candidates, and only keep the ones where there is an optical counterpart, then you push the contamination below 1%. Also in the X-ray, to a very good approximation, only the virial regions produce signal. The rest of the universe is dark. So in SC cluster cosmology, the primary challenge turns out to be not contamination, but mass calibration. And we're going to use weak lensing to solve that problem, and that's a problem that's getting easier to solve because of these large area, deep optical surveys. There is also optical cluster selection. There are other kinds of selection, shear peaks, things like that. The red sequence sample, I'm just going to talk about optical selection here. Red sequence selected samples, they have contamination also, or primarily, through what we refer to as projection effects. The problem here is that these red sequence galaxies live not only in the clusters, but they live throughout the universe, the so-called LRGs that were the focus of a talk of an analysis yesterday. And so when you look out into the universe, you see not only the clusters lit up with red sequence galaxies, but the large-scale structure and the surrounding intercluster spaces. And that makes it difficult to extract non-contaminated samples in the optical. So that's the main difference between SC and X-ray samples versus optical samples, the contamination. Why does contamination matter? Well, when you try to do the sort of analysis that Sebastian just walked you through, in order to do unbiased cosmology, you have to model the contaminating population as well. In addition, and so in the end, your cosmology is only as good as your contamination model is. And that's not exactly where we want to be when we're trying to do cosmology. The other thing is that the contamination, even if you model it perfectly, is adding Poisson noise to your measurement. Okay, so I'm just saying SE and X-ray cluster cosmology have certain advantages. Sorry. So next part of the talk then, the RASS plus DS cluster sample. So what we've done to try to understand how best to use DS together with the X-ray survey, for example, there's an upcoming eROSITA survey, the next generation X-ray all-sky survey, which I think Rishi talked about in the workshop. I'll say a little bit more about that at the end of the talk. But to sort of prepare for that, we used the old X-ray all-sky survey from ROSET. So what we've done is we've used the DS data, 5,000 square degrees, typical image quality of about 0.9 arc seconds as compared to the 0.6 or 0.7 from HSC. And they're about 2 magnitudes deeper than Sloan's. This is a very different data set than Sloan. It lets you study the universe to redshifts 1 and beyond, whereas Sloan is largely, for the typical galaxy population, is limited to the nearby universe. The ROSET all-sky survey, on the other hand, was an X-ray survey over the whole sky carried out in the early 90s. Over the DS region, there are about 20,000 sources, and about 90% of those sources are AGN. So only 10% are what we're after. We're after about 2,000 clusters out of the 20,000. The trick is to figure out which are which. The survey statistics here are 1.5 arc minute full width half max resolution. So that's adequate to resolve clusters from AGN for nearby clusters, but beyond about a redshift of 0.3, clusters in AGN look more or less the same. Okay, so here's just a map of the DS region on the sky, declination, RA, and what we've plotted here is the ROSAT exposure time. So another thing you have to deal with when you analyze this sample is that there are certain parts of the survey, this was a scan of the sky in ecliptic coordinates that are very deep near the ecliptic poles, and there are other parts of the sky which are shallow. There are other stripes here where basically ROSAT, the satellite, turned off, or there was high background or something like that. So there's quite a bit of variation in exposure here. Okay, so the way we're using these two data sets is this tool which we call the multi-component match filter, which basically is set to adopt a prior on the position of a cluster from the SE of the X-ray, take a position, then go into the optical catalog and basically scan through redshift and look for an overdensity of red sequence galaxies. All the details are here, but I'll skip them for now. I've mentioned this red sequence several times. Here's a plot from the DS data on known clusters, SPT selected clusters, of the deviation in color from the red sequence versus magnitude. And you can see there are no, I mean, this is just for qualitative purposes, that basically the cluster galaxies, a large fraction of them concentrate at a particular color. And if the resolution were a little better here, you could actually see that. You can just, when you look by eye at these clusters, you can see a bunch of galaxies of the same color. And we're using that fact to find peaks in the red sequence galaxy density as a function of redshift, okay? Because these, the color of the red sequence evolves with redshift. Okay, then here's sort of an example on 3 clusters of how this works. You basically scanning, here's Lambda, which is a count, an estimate of the number of galaxies in the cluster as a function of redshift. And you can see in this particular case, it peaks at a redshift of around 0.3, this case 0.4, this case 0.8. And again, if the resolution were a little bit better, you'd be able to even see by eye that these are very red galaxies and these are kind of yellow galaxies. And that's basically what the method is picking up, okay? So that's how we find these systems. That's how we optically confirm SC or X-ray selected systems. an important thing in a case where you have a highly contaminated sample, like the RAS sample, where 90% of our candidate systems are actually AGN, is the possibility of random superpositions, because the sky is just filled with these optical systems, these red sequence systems. 40 per square degree is a characteristic number. And so the probability of actually having a chance superposition of a noise fluctuation in the SC of the X-ray and some optical system is non-zero, so you really need to characterize that. And what we do is, to estimate this contamination, is we use the distribution of richnesses along random lines of sight, that's here in this lower line, and along the lines of sight to our candidates, our 20,000 candidates in the case of this RAS candidate list. And then by simply, if we know the richness of a particular system, this one is about 15, then we can simply integrate above 15, the random distribution and the candidate distribution, and we can say, what is the probability that this particular system is real or is contamination? And the example that's shown here is about a 5%, F cont of about 5%, corresponding to 5% random superposition. Now, in looking at this RAS data and X-ray selected clusters, we've been able to determine also that AGN often have IR sources, and there's a WISE infrared survey of the sky, another large survey, but in this case very shallow. And so for those clusters that have WISE counterparts, we look at their X-ray richness distribution, and some of them for their richnesses appear like clusters, and some of them for their richness, that is, they have X-ray fluxes that are, or X-ray luminosities that are appropriate for the for a cluster. And some of them, the AGN, have richnesses and associated X-ray luminosities that appear way too high. And so we're able to exclude those systems, and that allows us to cut out about 50% of the additional contamination. So an F cont cut of 0.05 leads to a final contamination of about 2.5%. So this is I think this is a step forward in what people have tried to do before. So what does our final sample look like then? So our cluster sample has about 2,000 X-ray selected clusters from RAS, or 1,000, depending on this F cont cut. So focus here, the number of clusters is listed here, the estimated contamination listed here. So if you want a very low contamination sample, we have about 1,000 clusters to offer you. If you can handle higher contamination, we have twice as many. And this just shows the redshift histogram of the samples with different F cont cuts. Now, for those of you who are familiar with the X-ray literature and work that's been done on RAS, this plot should look surprising to you for a couple of reasons. One is that there are lots of high redshift clusters out here. RAS is not known. RAS is a very shallow survey. eROSITA is meant to go 30 times deeper than RAS to push out to the higher redshift 1 and beyond universe. But actually, if you're careful with the data analysis with RAS and you go down to a 6 sigma selected sample, you have clusters in there out to redshift of 1. So with respect to the published earlier works on RAS, our cluster sample has about a 7 times higher density, 7 times more clusters per unit area, extends to redshift 1, and as I've shown before and emphasized here in this table, very low contamination if you select, if that's what you need for your analysis. Okay, and we have some pretty pictures here which aren't so pretty but on the screen, but will be on the web. I invite you to look later. Okay, so each of these MARD-3, so MARD year 3, because we've used the DS year 3 data, each of these clusters has a flux, a redshift, and therefore we can calculate an X-ray luminosity. And then using an X-ray luminosity mass relation, which we calibrated elsewhere in this Bulbul paper, then we can estimate the masses. And so we can create a plot, like Sebastian has shown from the SPT work, and the Plunk people have shown, ACT people. And you can see the distribution of the MARD-3 clusters here in blue. And you can see, for comparison, the SPT-SC distribution here. And you can see that this sample, in terms of mass sensitivity, the RAS sample plus DS has similar mass sensitivity out to about a redshift of 0.5. And the RAS sample is much more sensitive at redshifts less than 0.5, mass sensitive, and SPT at sensitive at higher redshift, just as you would expect But surprisingly, we've been able to populate this higher redshift space with the RASS dataset in combination with DES. We've done various validation tests. They're all described in this paper. We've compared to SPT, we've compared to Planck, we've compared to the MCXC catalog. We see no indications of contamination at higher levels than we expected. And in addition, then, we have made, so that gives us some confidence that the sample is clean. And so, given that we can calculate luminosities, and we have 1,000 clusters, then here for the F-cont of 0.05, 2.6% contamination sample, we're able to show luminosity functions for 1,000 clusters, or 1,100 clusters, in 9 different redshift bins. The points are the actual measurements from the MAR-D3 sample, and the lines are predictions, independent predictions, not fits to the data, of what the luminosity function should look like if we adopt the SPT cosmology, which we just heard is consistent with the Planck cosmology, and we adopt the halo mass function from Tinker, and we adopt the luminosity mass relation from Bull. So the fact that we have reasonably good agreement between our luminosity functions all the way out, well, we can't really call this, well, it's good agreement, but the constraints are weak. Let's say all the way out to redshift of 0.8, this is redshift 0.72 to 0.81, that's quite impressive. I don't think many people in the X-ray world would have believed that you could do this kind of work with the RASS data set. Okay, and we're trying very hard to do more sophisticated validation. That's coming, and we want to do cosmology, or try to do cosmology with this sample using DS weak lensing mass constraints. Running out of time, so the only thing I'll say about the DS weak lensing mass constraints is this one figure, which shows basically the stacked reduced shear, tangential shear, cross shear profiles for the 35% of the sample, about 484 MAR-D3 clusters, stacked, and you can see that there's tremendous amount of signal in here. Now, we're analyzing these systems cluster by cluster, and the constraints on a single cluster are weak, but there's a lot of information in here, and so we're quite enthusiastic about trying to put this weak lensing information together with the MAR-D3 sample to try to get a look at this X-ray-based cosmology. Just say a few words about this, and like I said, I'll skip this eROSITA part. The next part, I just want to show how DES and this MCMF tool are impacting the SPT sample. So we saw the core cosmology SPT sample in Sebastian's paper from this earlier survey between 2008 and 2011. But if you combine that with DES using MCMF, it improves the photoz's, and it allows us to push to lower signal to noise. So the red points here are the sample that Sebastian showed, and if you push down from 4.5 sigma to 4 sigma, you get these blue systems. Now, all of these red points were accumulated by specific pointed observations, optical follow-up, cluster by cluster. It was very painstaking, took years. The follow-up of the entire sample, once the DS dataset is in place, of course, the accumulation and the processing of the DS dataset took years too, but now that it's in place, this whole thing can be done in minutes, and we're able to add about 300 clusters to our SPT+SC sample. So we would have a total sample of about 816. Sebastian used about 400 of those for the analysis he showed before. One other plot, and then I think I have to finish. There's another survey, 500 square degree SPT poll, that's in the can. And if we do follow-up of that with the DS data set, then we produce an additional 321 clusters. Now, because the 500 square degrees of SPT poll was overlapping the 2,500 square degrees of the original SPT survey, not all of those systems are new. But because SPT poll pushed significantly deeper than SC, most of them are new. In fact, 112 are overlapping. And so if you combine all of these, the 300 new together with 321 minus 112, you get about 1,000 SPT clusters. And then there's a new sort of Summerfield, there's a different survey called SPECS, which should add about 300, and we're up to around 1,300. Okay, so with that, I think I've run out of time. I just want to invite you to look at the eROSITA forecasts. The summary would just be SE and X-ray cluster selection together with optical wide field surveys offer big advantages in cluster cosmology. Larger numbers of clusters, so more precise. Lower sample contamination, especially in comparison to optical surveys, so more robust cosmology. And the weak lensing mass information implies more accurate cosmology. So this is really looking good. Our demonstration on X-ray and SE, I was able to walk you through that. We have about 2,000 new RAS clusters, and we're doubling the SPT sample. And this last part, eROSITA, that sample should be 1 to 2 orders of magnitude larger still. The launch is scheduled for May of this year. And so I think that the future is quite promising for this particular probe of cosmology. Thanks for your patience.
Thank you for this very nice talk. So we're running a little bit out of time. I suggest we just have one quick question and then we save the rest for the break.
I was trying to look through your luminosity function plot, and it seemed to me that the prediction were slightly low in the lower Redshift bin, like first 2 lower Redshift bin.
That could be.
Yeah. So is that have you looked at the statistical consistency between prediction and the data? Because it seems all points are consistently above the...
So what we're doing in this so-called quantitative validation is to actually examine consistency between these points and the predictions. We can also allow the cosmology, we can allow the cosmology to float, we can allow the luminosity mass relation to float their uncertainties. The biggest uncertainty in this particular plot is this luminosity mass relation, and that's why we want to use the DES weak lensing to self-consistently measure a luminosity mass relation for this sample, and then replot these models. And we expect, we don't know, but we expect that the agreement would be better. But there's certainly no strong tension between the model and the data here.
Okay, let's save the next question for break. Let's thank Joe again.